Good morning, good evening, depending on where you're from, where you are. Today, I'd like to talk about something that I've been playing around for the past few weeks in FreeFlyer. Um, so this is basically an attitude control algorithm to get the satellites in alignment so that they can talk to each other. So a little bit about myself. I'm working as a researcher here in Pleiades Lab at Rome. Where we send a CubeSat every 2 years or so to perform experiments in space. So I've been working with FreeFlyer for more than a year at this point, but some of the key projects that I've done are using the FreeFlyer software to calculate the ground station service cost over 1 month, 2 months, 3 months, a few years, about 5 years. So how much would ground station service like the AWS or Leaf Space might cost the satellite companies over a period of time? And then considering that the second project, considering that we're all so excited to go back to the moon, I thought it would be fun to create a lunar rover and connect that using proposed 3-satellite ESA constellation around moon to connect that to ground station in Australia. The third one that I want to talk to you about today is the attitude control for optical communication link. Okay, let's get right into it. Why is optical communication needed? Why is there a rise in interest in optical communication? So while going back to moon, the NASA actually is doing many projects and trying really hard to get the optical link as standardized as possible to make it feasible in parallel with the lunar missions. So this is the article that you see that was recently a record of the highest transfer speeds that we have been able to achieve. So it's significantly good, better than what we have because it offers 10 to 100 times high data rates. It is because it's basically a laser. It's very well focused. It doesn't spread out, so there's less electronic interference or a chance that other countries or unwanted parties might listen in onto the conversations. So it's more secure and less prone to electronic interference. But there are challenges. One of them is atmosphere attenuation. So if there are clouds, or a bad weather, it's difficult for the laser to get through. And the second, we all remember playing around with lasers. They're very thin. So to connect two satellites with the lasers, we need the attitude control significantly accurate so that the other satellite basically the two satellites are aligned within that laser. So accuracy requirements. Let's talk a bit about this. The two satellites, as you see here, these are photos from the simulation that I've made. So spacecraft ISS or TDRS, these are just placeholder spacecrafts. I thought it would be cool to look at ISS than, say, a CubeSat. That's all there is to it. The process of acquiring the signal. So each of the satellites have attitude control actuators that can achieve a coarse control, maybe a little less than a degree. And once the coarse pointing is done, we need to execute a finer adjustment, which is less than 2,500 microradians, which is very thin. And this is done by using a highly collimated laser that could use a concept called waveform matching to track the controller satellite. Once the satellites are within that range of 2,500 microradians, then the alignment is further fine-tuned so that in the data trace transfer phase, they are aligned with 10 microradians. So even in this, moving from data acquisition phase to the data transfer phase, signal acquisition phase to data transfer phase, we're going 250 times more accurate. So this is something that is incredibly challenging with the optical communications. So at the moment, the satellites can course control based on the star sensors, other attitude control actuators, about 100 millirad, more or less. But what we need is to get the satellite pointing within that laser thickness over huge distances within the 10 microradians. So the simulation that I want to do is to achieve this attitude alignment through one axis, which is for the first step, which is course control. Okay, we'll get to the simulation just in a moment, but before that, I want to explain why I choose Python and FreeFlyer interface for this mission. First, in the lab that I work, we build telemetry software at the lab itself. So everything is done in Python, and we have libraries to build software that could read, that could decode information and display on the software. So because of that reason, I thought it's good to have a FreeFlyer interface that we could interface with that software if need be. So we could leverage the FreeFlyer engine directly from our software using a Python library called Runtime API. So once we have built the baseline, we could actually simulate few command situations. So if I send the attitude command, I could ask FreeFlyer for information on how much time that attitude control maneuver might take. Things like that could be an added feature if I use Python directly from my software. One other feature that we've been trying to implement in our software is near real-time visualization with the telemetry that we receive from the satellite that we send. So this is also like pretty straightforward from the FreeFlyer interface to be executed. So that is an added advantage to work with Python and FreeFlyer interface. So in real case, in real life, the way that we could do this is to get the telemetry from the satellite, which gives us the current attitude, then send that attitude to the FreeFlyer algorithm, which would execute the control algorithm and achieve the desired attitude, which is mentioned in the FreeFlyer. After the end of the simulation in FreeFlyer, it sends back the attitude parameters for Python so that it could communicate back to the satellite. So what I'm going to implement is a single axis control scheme, and the attitude requirement is less than a milliradian. But the current simulation, at the moment, we don't have any satellite in space. So I took the current attitude directly from FreeFlyer. So I defined a satellite with a certain attitude, and I get that attitude back to Python. At which point it will decide whether to implement this loop or not. So if the attitude is bigger than what the desired attitude or what the defined attitude in Python is, then it triggers a control loop from FreeFlyer in FreeFlyer, which runs the control algorithm and gets the attitude in the desired range. So as I said earlier, it's basically I used the ISS 3D model, but it cannot actually do a 60 degrees rotation. What it's meant for, what this algorithm is also desired as a final step, is within a degree. So I want to get the execute the attitude control not more than a degree, but less than a degree. But for the simulation, a 60-degree slew looks good than 1 degree because because it's actually visible. So to do this, I defined a custom coordinate system. This is something that you can do in FreeFlyer with a single line of command. Once we define the vectors, so I defined a vector joining the 2 satellites, and another vector joining the space station and Earth. Once that's done, I can then define the coordinate system. I define the attitude of the spacecraft in the custom defined reference frame. And then the PD controller is based on this reference frame and the attitude defined in this reference frame. All right, so because we're done with the theory, let's take a look at what the simulation I ended up with. So what you're looking here is around the x-axis, assume that there is an antenna, and I want to align the x-axis of the spacecraft ISS with the x-axis of TDRS. Okay, so the ISS to TDRS is the vector that is directly connecting the space station to TDRS. So if the x-axis is finally at the end of the control loop, perfectly aligned, or at least closely aligned with ISS to TDRS, that's the final goal. So that's what we're looking for. Let's see. All right. So that now is within a milliradian, which was the requirement that we started with. So this took about a day to run, but let's take a look at the same thing from another angle. So again, we're just to remind, we're looking at the x-axis to be aligned with ISS to TDRS vector. All right, so that took about 1 day, as I said, but by changing the control parameters and keeping, after a bit of trial and error with the ratio of KP over KD of 100, which is basically there are 2 parameters in control that I used for the proportional and derivative. If the ratio was maintained 100, then I could get the same 60-degree slew within 3 hours. So I wanted to show you how a run directly from Python would look like. So this is the Python code that I wrote for this program. So I run it. I apologize, it's slightly slow. It's just because of my system, but all right. So the earlier graph that we saw was exactly this, or I could run it just to show at least from this point. So we started with these are the 3 angles that are made with the 3 axes. And as you see with the control algorithm, the 3 axes, the 3 angles are over the course of 1 day being reduced or brought back completely to 0. So these are the final results of the three angles, which I named alpha, beta, gamma. And then after capturing these videos, I was able to do this even at a faster rate, which was about 3 hours. All right, so future developments, I had a few ideas on to how to improve this project, or how to build on this project. So I executed the course tuning. I want to try and run a fine tuning of the attitude, which is more accurate, by optimizing for the transmitted power. So FreeFlyer can do RF link analysis, where it measures the received power as well. So I want to see if I can push the algorithm enough so that I can get the fine tuning that I need. Second, I want to implement a 2-axis control. So now I only executed 1-axis control, which was x-axis of one satellite pointing to the x-axis of another satellite. But what if there's a requirement or that the camera has to be pointed in a certain way? So for example, there's a camera on y-axis that I want to take pictures of Earth and simultaneously communicate with the other satellite. So I would like to have that constraint, and that's something that could be a interesting thing to simulate in FreeFlyer. And repeat the study with using real actuators that are available in the market. This could lead to a slower response or a faster response. I didn't actually try this one out, but I would like to see how that would that change the response response time that we have. And if you have any interesting ideas, do drop me a message on LinkedIn, where I have the LinkedIn profile attached here. So in conclusion, by doing this project, I wanted to simulate a communication, understand how Python and FreeFlyer would talk to each other, and how that could be leveraged to build missions in Python. And that was achieved. And second, by the end of the project, I was able to get 60-degree slew within 3 hours, although it's simulated, but it's an improvement than to the first one day that I had through the simulation.